Hello everyone. First I have to see how it works. It's switching. My name is Reza Talemi from Huylebroeck from Belgium. So today I'll share some initial results that we got on this topic, which is work of my former PhD student and former master student, which is working already in our group for a year. You have heard a lot about additive manufacturing actually up to this point today. That's a lot of talks about additive manufacturing, and there are a lot of potentials actually in the industry. One of the greatest potential of the additive manufacturing is this internal features that you can create, which is not possible or very complex to create using conventional method of manufacturing. We thought how to integrate this with the fatigue and fracture, let's say, concept, and how to improve some fatigue life of some components by adding some internal features. So today we try to tackle this problem, and I will show you some results about the, let's say, effect of internal grooves or internal features on fatigue behavior of additively manufactured part. In the first place, we try to do that numerically. So then what you see here, first I will talk about the motivation and objective of the work, and then I will talk about the numerical modeling approach that we used, and then the results and discussion, and at the end I conclude some initial results, but of course some ongoing research should be discussed as well, which I will communicate with you. The motivation comes from one of the papers that we published 2 years ago. In this paper, we tackled a complex problem of, let's say, shrink-fitted connection. Here you see a shaft, which are shrink-fitted together. And here we have, at the contact side, we have very high stress gradient and very high stress concentration. So the idea was how to improve the lifetime of the fatigue lifetime of this shaft. And then we thought about, okay, could we use some additively manufactured shaft there and introduce some internal feature like this, like a keyhole that you see here. Because of the high stress concentration that we had here at the contact interface between the hull and the main specimen, then the idea was to have a kind of stress relief groove there. And it worked actually at that time. We numerically investigated and we found out that the fatigue initiation lifetime can be improved by a factor of 5.6, and then crack propagation also 1.5. So that was a big achievement at that time, but I was not sure. I was not really sure about the numerical data and the way that we can do that. So then the main objective of this work is to see a very classical problem of fracture mechanics, like, for example, a dog bone shaped specimen. And then we put a kind of notch there. And then we have a kind of internal, as I call it, a donut shape, or it can be called truss, let's say, shape, which is manufactured using additively manufacturing technique. For example, it could be laser powder-based fusion technique. There are two problems with that. The first problem is, okay, where should it be? Where is the location which gives us the higher fatigue lifetime? And what do we do with the powder which is not melted actually? There are two possibilities to deal with the powder. First possibility is to put the powder there and do not touch it, so it's not melted, but it's a soft inclusion. The second possibility is to put a channel there in a design and remove the powder and suck it out after that. At this point, we just said that, okay, let's the powder stay there, and then we try to focus on the numerical side and find out where is the optimum location. So that was the main objective of this study, to find the optimum location and shape to improve the fatigue life of a dog-bone-shaped specimen. To do that, we tackled the problem using a rotating bending fatigue machine, or at least loading condition at this point. And this is the geometry of the specimen that we try to solve. So we create a notch here. We try to have two different types of notch, let's say shaped notch and a U-shaped notch. And then for the V-shaped notch, we try to have kind of radius here at the notch tip. And then we try to have two different possibilities, a truss and a keyhole internal groove. The parameters that we wanted to control are D and L, so the position and then the diameter. And for the keyhole one, we have D, W, and L. So basically 2 parameters for this elliptical shape and then 1 parameter for the position. We developed some numerical codes first to understand what could be the optimum situation. So the 3D model was developed. We developed a 3D model, and we tried to have a minimum mesh size at the notch tip. So 3 micrometer by 3 micrometer, let's say, mesh size, and we fixed one side, and then we applied the cyclic load at the other side. So the diameter of the specimen was 9 millimeter, and then we only modeled the gauge section, which is 20 millimeters in this case, more or less. And the stress was changed between 200 megapascals and 400 megapascals, and we stayed at the, let's say, elastic regime, so then we targeted high cycle T. Then we used some critical plane approach, in this case stability parameter, to find out the maximum damage actually at the notch root, or if it has been shifted to the site of the internal groove. So we were not sure about that. The material that we used was stainless steel, and these are the material properties. So we ran actually 166 simulations with different combinations to find out what is the best location for such a notch. Here are some initial results that we got. So then here is the 2D view of the setup that we developed, and here is the stress concentration, and let's say we calculated the number of cycles based on the damage stress that was accumulated underneath or above, depending on the cycle. These are the best case scenarios that we could get. First of all, in none of the 166 simulations, the stress concentration moved to the groove side. So it was always at the notch side, so never on the groove side. So it means that it would initiate always on the surface. Here you see some one misses stress distribution of different conditions, and in this case the best conditions that you can get for the U-shaped notch, and this is the best case condition that you can get for let's say V-shaped notch. And then here we have a keyhole, and here we have a truss, let's say internal groove. But these are the outcome, the final outcome that we could find, but we did, as I said, more simulations, so we tried also to monitor and see what would be the effect of different parameters, and why there is a variation, for example, if we change D or L. On the left side, what you see is the reference. Here is the reference SWT, so without any internal groove, only with notch. So that was the damage that we could get. And here is the stability parameter L and D for the V notch, and here it's the same for the sorry, here U notch, here V notch. And then we try to monitor the stability parameter at the root of the notch, and see what would be the effect of the diameter for in both cases, and then the variation of this L value. And we see some fluctuations in some cases. The best case scenario that we could get gave us the stability reduction to 0.19 for the V-shaped notch and U-shape, and for the V-shaped notch we got to 0.39 compared to the reference one that we had. But the fluctuation also exists in both cases. So we had a little bit change of the L value could give us a higher or very lower stability parameter. So it was not easy. It was not a smooth transition. So it depended a lot on the on these two values. In the first place, we thought it might be mesh related, so we did also a mesh convergence study just to be sure that we have a kind of uniform mesh. So there was no effect of mesh at that point when we checked. For the keyhole notch, it was a little bit more complex, so we could not do the 3D, nice 3D graph. So what we did was we focused actually on these kind of tables, and we found out that okay, the variation is quite high. For the V notch, and for U notch it was better, a lot better actually improvement. So here what you see is the percentage of the decrease or increase of the damage parameter stability in that case. And the best case that we could get was 15% improvement, or let's say lower damage for the keyhole, these dimensions of keyhole for V notch, and for U notch it was around maximum 12%. Knowing all these, we picked the best case scenarios, and we tried also to predict some ascent curves, some virtual ascent curves if you like. So here I have coded them, so then from 1 to 4, what we see here is the ascent curve. So we repeated the same test, the best case scenario, and we compared that with the notched and V notch and U notch as a reference case here. And then we tried to target the 10 power 6 as a fatigue limit cutoff, and then we also compared the fatigue limit improvement that we can get with this kind of internal groups. So what you see here, in this case, we got some improvements, but it's not that much. So from fatigue limit point of view, the best that we could get was around 13.5. So it's not comparable with what we observed for the, let's say, press-fit connection, which was around 5 times higher. But it's something that we can work on. The next step was to see, okay, this is pure numerical approach. Can we really print such a small notch in reality? So the next step was, So the next step was to go and print them. So what we did, we just designed, like it is typical for 3D printing, so we design, you design a CAD model, so here from 100 to 500 micrometers, let's say internal grooves, and then the same process of 3D printing. I'm not going to go through that. And then we expected to see some rounded, nice internal groove. We used one of the best, let's say, printing machine that we have in the called Leuven's AM lab. And then these are the printing parameters. They were optimized for the same material, and they were tons of data produced for the same material before, and it's the best that they offered to us. But this is what we got at the end. So here are the real holes. So from 250 micrometer, you could see something. The rest, the powder was not lasered, but it was melted. And then these are the, let's say, the real printed shapes, and these are the designed actually shapes from 0.5 millimeter to down to 0.25 millimeters. And then next we used the real shapes. So we said that, okay, let's simulate this one, this real shape, so this awkward shape, and then we simulated that. And then here is the final result that we get at this point. So what you see here is the normalized fatigue lifetime, and then the crack. The ratio of the, let's say, the printed one and the designed one are not following the same trend, as you can see. In some cases, 0.25, they are concentrated, so it's okay. But in some cases, for example, for the V notch, you see that the designed one are better, but the printed one are worse. And other way around for the U notch, so we have some, let's say, worse result for the designed one, and then a good result for the predicted one. But that gave us the idea that we could have a kind of optimal geometry for that. Why not having kind of a kind of weird shape, which is calculated based on topology optimization, which would be the next step. So I'm done here. So then the main idea that we had, it works. So then there's an improvement, but it's not that much as we observed in the first study. Then we realized that printing this small, very small 100 to 500 micrometer internal groove is very challenging, but could be done, but with some modifications. And the next step is to validate the fatigue data that, or the numerical result that we obtain against the experimental test. That's it from my side. I will be happy to answer your questions.
Thank you, Reza. Any questions from the audience? Please, Professor.
Yes. It's a very nice idea, but could you explain what is the criterion of the numerical code that the specific configuration attain the critical limit for crack propagation or fatigue life? What is the natural criterion?
It's a critical distance approach.
Critical distance.
So then we monitor the critical plane on the notch tip, or in the first stage in the entire specimen, and then we realize that it's always at the notch tip, and then we monitor the stability parameter, which is based on the maximum stress applying on the maximum principal strain plane. Do I have it here? So this is the stability parameter.
And what are the natural meaning of these constants, B, C? How they
These are the
defined?
fitting parameters from
Just
the
fitting parameters.
yeah. These are for the fatigue lifetime predictions. But in the first place, we focused only on the damage parameter. So the damage parameter does not include any let's say material parameter. But when we wanted to predict the lifetime, the ascent curve, then we had to use some sort of the other side of the
How do
equation.
you define the critical constant, B and C?
It's taken from the literature from the same data which is 3D printed. So then we had, as I told you, that with the machine that we used that a lot to print the same material and to characterize that, and all the parameters were optimized, and then we also used the same parameters that we could get out of this strain control test.
So, thank you